Hello dear students, welcome to your very own physics channel. It is Physics I'm your physics teacher Hemen Chaudhuri, and we are going to learn today the Pulley constant equations. So let's start with a very simple example. So students, I have already drawn this diagram for a pulley system. It is very simple pulley system. You have two blocks over here, M1 and M2. And suppose M2 may be going downward and M1 may be going upward. In both the cases, the string length will never change. The string length will always be constant. Whatever be the displacement of M1 block or M2 block, the string length will never change. Suppose for this region we have x1 plus x2 equal to L. Now with respect to time, if you differentiate this equation, what will you have? You have dx1 by dt plus dx2 by dt equal to 0, because the length of the string is constant. So when you differentiate this, you will get 0. So from this equation you will have velocity v1 plus velocity v2 equal to 0. Students, if you differentiate this equation again with respect to time, you will get acceleration a1 plus a2 equal to 0, and suppose you can write like this, a1 equal to minus a2. This equation means the acceleration of both the two blocks M1 and M2 is equal, but if one is moving in the upward direction, the other one will be moving in the downward direction. That means the acceleration of both the two blocks will be in opposite direction. The student, this is a lengthy way to find the acceleration relation between these two blocks A1 and A2. We can find this one with a very simple approach. Let's start this. Again, I am drawing this pulley system. This is our pulley. This is also our pulley system. It is suppose again M1 and this is suppose M2. Now in this approach we will not go like this. We will see the tension direction on these two blocks will be what? It is always away from the body. All you know all about this. So tension is always away from the body, and suppose this block is moving in the downward direction. Suppose this acceleration is A, and suppose it is A2, and for this block, suppose it is moving upward direction, it is A1. Now see this, then tensions are your internal forces, and you can just consider these are forces and these are your acceleration. So work done on the system is always equal to 0. So what you will have, suppose we find the work done by tension on the blocks, then you see on this side of block M1, what you will have? Tension and acceleration are in the same direction. So if you take the dot product for work done, what you will have? T A1 cos 0, and on this side what you will have? The acceleration and the tension is in the upward direction. So what will you have? T A2 cos 180 degree. Now you see cos 0 is 1, so from both the side tension and tensor get cancelled, so you will have A1 equal to minus A2. So student, this system is very easy for us to find the acceleration between the given blocks in a very simple manner and in a very quick time. So for your exam also this system will be very helpful. Now see this system a bit one again. Now move on to this example and we'll apply this concept only on this system. In this system also you see student, the acceleration of this M2 block is suppose in the downward direction, it is A2, and for this system M1 block is moving in the right way. So suppose this acceleration is A1, and since the string attached to block M1 and M2, it is the same string, so tension will be same in both the string. Tension will be same in both the string. Again you apply this concept. Now see, for this system what you will have? Tension and acceleration are in the same direction. So what will you have? T A1 cos 0 is equal to, again you will have T is in the upward direction and acceleration is the downward direction. So you will have T A2 cos 180. So you will again have A1 equal to minus A2. That means in this case also we can find the acceleration is very quick way like this way. Now student, let's start this example. This is a block M1, and in some book it may be written like a plank, and it is suppose block M2, and this is your block M1. In this system also we are going to apply the same concept like this one and this one, and it will have very easy way to find the acceleration between this M1 and M2. Now say student, the acceleration for this system, you want to find the relation between A1 and A2. First you consider this one. Suppose you will have M2 is moving suppose in the downward direction. Suppose it is A1 and it is suppose A2, or we may say consider this is suppose acceleration A1 for block M1 and it is suppose A2 for block M2. Now say student, the tension is in this case from this point up to this point, this is the same string. So let us consider the tension as T and T, and it will be away from the bodies. So if this T and this T is here, then what will be the tension at this point? It will be your twice T. Again, if it is twice T, again from this position up to this position, this is your same string. So in this case also you will have tension as twice T. So now if you have twice T on this part and twice T on this part, what will be tension for this pulley? It will have 4T. And if you have 4T on this side, this is also your same string up to this position, so you will have again 4T tension for this part. Now students, see what is the work done on this block M1. It is, suppose you have A1 as acceleration, and what are the tensions? It is 4T in the upward direction, again 2T, again you have T. And on the M2 block, what you have? You have T, only you have T, and on this side you have only A2. So for this system, what you have? You can say here cos 180, and for this you can say it is suppose moving upward, it is A1 and the summation of this all tension. So what you will have? A1 into 7T equal to A2 into T. So both this side you have tension get cancelled, so you can get A2 equal to 7A1. So students, I think you have understood both these three examples and its numerical process. In the later class, we'll take some more example and just follow my lectures and study them. Okay, thank you so much and keep on studying.